In this section, we will discuss Gauss theorem and its various applications. In this episode, we will be concentrating on two applications. First one is, we will try to derive Coulomb's law from Gauss theorem. And second is, we will try to find an expression for the electric field at a point due to line charge distribution. Right? So let's concentrate on this, derivation of Coulomb's law. We are aware Coulomb's law is applicable for any two-point static charges. It's the basic law in electrostatics. In case those 2 point charges are placed in air or vacuum, then the magnitude of the electric force between them is given by F is equal to 1 over 4 pi epsilon naught Q1 Q2 by R square. So let's derive that mathematical expression using Gauss's theorem. Right? Let us consider charge Q1 to be placed in air or vacuum. Let P be any observation point which is at a distance R from charge Q1. Now, in order to determine the electric field at point P due to this charge Q1, we can make use of Gauss theorem. Now, students, do remember, in order to apply Gauss theorem, we need a Gaussian surface. And Gaussian surface, as I told you earlier as well, it's an imaginary surface which encloses any net charge. For a point charge, obviously we will consider spherical Gaussian surface. For line charge, we may consider cylindrical Gaussian surface, isn't it? So presently there is a point charge. So taking point O as center and OP equals to R as radius, we can draw a sphere. Since it's imaginary, so it will be represented by dotted lines. This is a sphere. So this is a Gaussian surface. This is a Gaussian surface which encloses some net charge. Now this closed surface encloses net charge Q1, right? So we'll consider a small elementary portion. Elementary portion is to be always considered of the Gaussian surface. This we represent as ds. We know in the case of a perfectly spherically symmetrical surface, area vector is always in the radially outward direction, along the radius and in the outward direction. Now due to this charge Q1, which is assumed to be, for convenience, assumed to be positive, the electric field would be also in the radially outward direction. This is the direction of the electric field. Fine? So the angle between these two is 0 degree. Now, using Gauss theorem. We are aware Gauss theorem states that electric flux, which is numerically equal to the closed surface integral of the electric field, is numerically equal to 1 by epsilon naught times the net charge enclosed. Here the net charge enclosed by this Gaussian surface is Q1. Fine? So let's evaluate it. What's the angle between E and ds vector over here? It's 0 degree. So we get E ds cos 0. Make use of the property of scalar product Q1 by epsilon. Electric field at any point on the surface of the sphere being equidistant from charge Q1 would be constant. So it can be taken outside the integration. So integration ds, that obviously would give us the total surface area of the Gaussian surface, which in this case is spherical. And of radius r, the total surface area of a sphere is 4 pi r square, right? So we get E into 4 pi r square is equal to Q1 by epsilon naught. Therefore, electric field at point P due to charge Q1 is Q1 divided by 4 pi epsilon r square. This we are already aware of. Put this as equation number 1. This is the first step. Now what to do is, place another point static charge Q2 at point P. I repeat, place another point static charge Q2 at point P. Now this charge Q2 under the influence of electric field E due to charge Q1 will experience an electric force which will be given by F is equal to Q2 multiplied by E in magnitude. Look, electric field at this point is given by electric force per unit charge. So the electric force experienced by this charge Q2 at point P due to charge Q1 would be given by F equals to Q2E, right? Now what you need to do is simply substitute this value of E over here, you will get the expression for the Coulomb force. So we get from 1 and 2 we get Q1 Q2 divided by 4 pi epsilon r square. So this is the mathematical expression for Coulomb's law. So this is a very simple mathematical verification of Coulomb's law by using Gauss's theorem, right? This is the first application. Let's consider the second one. For a point charge, we are aware of the expression for the electron. It's simple, kq by r square. But for complicated system of charges, like in case of line charge, in case the charge is distributed over an area, then the expression for the electron field becomes complicated. It can be made simpler by using Gauss's theorem, right? So, proceeding, let's consider this particular article now. Electric field at a point due to line charge distribution. This is an infinite long line, and suppose charge Q is uniformly distributed over length L. We have already discussed this. It's a case of one-dimensional, right? So we'll make use of lambda, which is linear charge density. So linear charge density would be Q by L. If the length increases, the charge contained or uniformly distributed over it will also increase. So it is immaterial whether to take the elementary length shorter or longer length, right? So this term will always remain constant. In case L increases, Q will also increase in the same proportion. So Q by L always remains constant. So this is the line charge distribution where we have discussed charge Q to be uniformly distributed over length L. This is the length L, right? Now my objective is to determine the strength of the electric field at point P due to this line charge distribution. It's a complicated case, right? But by using Gauss theorem, this article can be made very simple. So what to do is, I've always told you, before you make use of Gauss theorem, you need to consider a Gaussian surface. It is only when we consider Gaussian surface, then only Gauss theorem can be made to be applied. So for line charge distribution, we will consider a cylindrical Gaussian surface. So taking this as the axis of the right circular cylinder, we will consider point P to be lying on its curved surface. So the diagram will be somewhat like this. And since Gaussian surface is an imaginary surface which you are considering, therefore it is represented by dotted line. So this is a right circular cylinder, say of radius r, the distance of the observation point from the axis, right? And this is it. This is the right circular cylinder with this constituting as the axis. It has got three surfaces. This one, let's consider this to be 1. Let's consider the curved surface to be 2. And this again, flat circular face to be 3, bottom one. Now, this is line, consider this to be line, one-dimensional thing, and charge is uniformly distributed. Positive charge. So due to this line charge distribution, electric field will be in the radially outward direction. It will be in the radially outward direction, like this, along this direction, isn't it? So that is what I am going to represent over here. So this will be the direction of the electric field, like this. It would be in the radially outward direction, perpendicular to the surface. This perpendicular to the surface. Right? This is the direction of the electric field, like this. It's in the radially outward direction, making an angle of 90 degrees with the curved surface, like this. Now, in order to find the electric field at point P, let's make use of Gauss theorem. Again, Gauss theorem, it is stated as electric flux linked with a closed surface. It is given by closed surface integral of the electric field, which is numerically equal to 1 by epsilon times net charge enclosed. What is the net charge enclosed by this closed surface? It is considered to be Q. Right? This is Gauss theorem. Let's start evaluating it. It is for closed surface. It can be bifurcated into three plane surfaces. Two top and bottom circular faces, and the third one curved surface. Right? So it can be bifurcated like this. E vector dot ds1 vector for the first plus E vector dot ds2 vector for the second one, and third one E vector dot ds3 vector for the third one, and it is equal to Q by epsilon. Now look, ds1, this comes to be 1, so ds1 needs to be this one, area vector, this is ds1. Area vector again I am mentioning time and again. For this area, top circular face, the area vector would be in the upward direction, perpendicular to that surface. For this one, this is a curved surface, this is considered the second one. The area vector would be in the radially outward direction. This is ds2, right? And for the third surface, bottom, it's again in the radially outward and in the outward direction. That is, in this case, it will be in the downward direction, like this. This is ds3. Now look, electric field lines will be like this. As I told you, it will be like this. Consider top and bottom faces. The field lines will be along the top and the bottom face. That is, those two faces will not contribute towards the flux. What I mean to say is that, what's the angle between electric field vector and ds1 vector? It's 90 degree. And scalar product of two perpendicular vectors is always 0. So this term won't contribute anything towards the net flux, because electric field lines will pass through the surface along this surface. Here also this face, the area vector is in the downward direction, while electric field is in this direction. So the angle is 90 degree. So electric field lines being along the bottom circular face, this face will also not contribute anything towards the flux. So these two terms will not contribute anything. So what you get is, this term will not give any resultant, because the angle between these two is 90 degree, the angle between these two is also 90 degree. And consider the second one. Electric field is in the radially outward direction. So what's the angle between electric field and this area vector? This is the direction of the electric field. Along this direction, outward, it's in the radially outward direction. So angle is 0 degree over here. So what I mean to say is that, consider the curved surface. All the field lines from the line charge will be crossing the curved surface in a direction perpendicular to it. So it is only the curved surface which will contribute towards the flux, right? So this is the term which we get. E integration ds would be 2 pi RL plus this term won't contribute towards anything, and it will be equal to Q by epsilon naught. Now look, electric field can be taken outside. Why? Because electric field at any point on the curved surface of the cylinder being equidistant from this line will be constant. So I have taken it outside the integration. Dot product of these two, since the angle between these two is 0, cos 0 becomes 1, so we will be left with E ds. E can be taken outside the integration, and integration of ds2, that will give us the total surface area, curved surface area of the cylinder. And curved surface area of the cylinder is 2 pi RL. That is what I have written over here, right? So we are left with E into 2 pi RL is equal to Q by epsilon. So if you substitute the value of Q as lambda L, what you get is E into 2 pi RL is equal to lambda L divided by epsilon naught. So L will get cancelled. We will be left with electric field is equal to lambda divided by 2 pi epsilon R. This is the formula for the electric field at a point due to line charge distribution. So you can very well conclude, for a point charge, electric varies with distance as 1 by r square. For line charge distribution, electric field varies with distance as 1 by r. So this is a very, very important conclusion. For point charge, we are aware electric field varies with distance as 1 by r square. While for line charge distribution, just now we have discussed, electric field varies as 1 by r. Lambda is constant, it is the linear charge density. We can also draw a graph showing the variation of electric field with distance r in the case of line charge distribution. So it is like this. Let us consider the x-axis to be represented by distance and electric field be represented along y direction. Now E is inversely proportional to 1 by r. So if r is 0, E becomes infinity and vice versa. So the graph would be like this. It will touch at infinity. It will touch at infinity. So E is proportional to 1 by r. So this graph shows the variation of electric field with distance r in case of line charge distribution. So there are other articles as well which we'll cover in the next episode.